The HR diagram is so important that I felt I had to go over it with you, even though my art skills are non-existent. So please look at the much better diagrams in the textbook. The basic idea is that stars come in different surface temperatures. We figure out their surface temperature by looking at their spectra, at the light that they emit. Now, for historical reasons, the spectral classes are O, B, A, F, G, K, M, with some newly discovered ones further on for very cool stars and things that never became stars, brown dwarfs. Originally, they were in the right order alphabetically, but the wrong order in temperature. We put the hot ones over on the left and the cool ones over in the right. Stars also come in different energy outputs, in different luminosities. Think of them as light bulbs with a different wattage. Remember that absolute magnitude is a way to describe the true energy output, the true brightness of a star. We put the dim ones here and the bright ones up here. And what was discovered was that about 90% of the stars in our galaxy fall along this diagonal line. That means that it is normal for a star to be hot and bright, cool and dim, or medium temperature and medium brightness. This is where all of the happy, healthy adult stars live. All the stars that are converting hydrogen to helium in their core. We'll come back to the importance of that in a different video. All right? Any star that is not on the main sequence is in the process of dying. It is not a happy, healthy adult star. It is not converting hydrogen to helium in its core. Right? We have stars over here that are cooler than average, but they are brighter than average. So how do they compensate? They compensate by being a lot larger. And especially since these are cool and large, not only do we call these giants, but specifically often called red giants because they are cooler stars, they are redder in color. The hotter stars are bluer in color. Right? To give you an idea, if our sun were replaced by a red giant, it would fill up so much space that it would swallow up Mercury, Venus, and Earth. There are stars that are even larger than that. How do we know they're larger? Because they're even brighter at the same temperature than the giants. So again, to get that incredible brightness, they have to overcompensate by being ginormous, literally. If we replaced our sun by a supergiant, it would fill up so much space, it would swallow up Mercury, Venus, Earth, Mars, asteroid belt, and in some cases, Jupiter. Okay? That's a ginormous star. Very unhappy, big, bloated, dying star. Down here, we have a completely opposite extreme. These are stars that are very hot, but yet they're not very bright. So what's preventing them from being bright if they're so hot? Well, they must be very small. So even though they're very hot, they're not very bright because of their small size. And because they are white hot, and because they are small, they're called white dwarfs. White dwarfs represent the endpoint, the corpse of stars of low mass like our sun. Our sun will eventually become a white dwarf. More on that in another video. How small are white dwarfs? Well, they're about the same mass as the sun, but they take up about as much space as the Earth. Imagine something that weighs as much as the sun compressed down to the size of the Earth. It's incredibly dense. It's the incredibly dense corpse of a star. So where would our sun be? Remember the Goldilocks paradigm? Not too hot, not too cool, not too big, not too small. Just right? Well, that's where our sun is. Our sun is a G-class star. You are here. Now that's a good thing, because if our sun were too cool and dim, well, we'd all freeze to death. And if the sun were hot and bright, we'd all boil. So the fact that our sun is just right means that we here at Earth, at this distance away from the sun, have the temperature needed to sustain life.